All right, howdy physics class. Mr. Wood coming at you from my basement. The internet wasn't working up at school, so here I am. Doing more conservation momentum stuff, just a couple of more practice problems that to give you just a little better idea of how to do this. Going to work through several of them with you. Here's our first one, problem one. 1,000 kilogram car traveling south at 20 meters per second collides with a car traveling east at 20 meters per second. The two vehicles entangle after the collision and head off as one. What is the velocity of the combined wreckage immediately after the collision? So, just like before, we have masses, we have velocities of vehicles. So, before the collision, we have object A with a mass of 1,000 kilograms, object B with a mass of 1,200 kilograms. Both of those have velocities. Velocity A was 20 meters per second southward. B was 20 meters per second eastward. All right, so far so good. After the collision, so this is our after time, we know that we have the two cars together as one, so we have a combined mass. We'll call that mass total, and that'd be 2,200 kilograms. And we have some new velocity, velocity prime, that is our unknown. That's what we're trying to find. So nice thing about this, it's all right angles already. So right now I know I have one vehicle going straight to the east. I suppose I should do this first. Remember, we don't have a conservation of momentum. We have a conservation of momentum, not conservation of velocity. So the momentums here, momentum of A would be 20,000. That's kilogram meters per second. And momentum B should be 24,000 kilogram meters per second. And of course, that is south and east. East, respectively. So back to our diagram. We have a momentum going to the east of 24,000. We have one going to the south at 20,000. And our resultant then, combination of the two, right there. And we know that this is a right triangle because south is 90 degrees from east, right? So a squared plus b squared is c squared. And so our total momentum would be equal to a squared plus b squared. Square root of that. And I get the momentum total to be, lost it here, 31,240 kilogram meters per second. Of course, we're not looking for a total momentum. We're looking for our new velocity. So we need to divide that by the combined mass, which would be 2,200. So I get a velocity of 14.2 meters per second. And then, of course, since this is a momentum problem, velocity by itself isn't enough. We also have to have direction. So we're looking for this angle here. We'll call that theta. And, of course, tangent of the angle theta is going to be the opposite. The adjacent. So theta is then 39.8 degrees, and that would be south of east. So those two combined is your answer. All right, so that's the first problem. I'm going to take a quick break here, and I'll do problem two. All right, we're back, and I'm going to work through problem 6 with you, a substantially more difficult problem. So work through this one with you. Hopefully it won't be too bad. So, number 6 says we have a 200 kilogram bomb moving with a velocity of 10 meters per second to the west that explodes into 3 pieces. The first piece has a mass of 100 kilograms, moves to the west with a velocity of 90 meters per second. The second has a mass of 55 kilograms, moves at an angle of 30 degrees north of east, with a velocity of 55 meters per second. And then what is the velocity of the third piece? So, a little bit different this time, but we start out the same way. Beforehand, right, we have a mass of 200 kilograms and a velocity of 10 meters per second west. So that would be a total of, right, so hold on. So that would give me a total momentum of 2,000 kilogram meters per second west. Okay, so that is beforehand. Afterwards, we no longer have one piece, we have 3 pieces. So we have pieces A, B, and C. The mass of the first one is 100 kilograms. The mass of the second one was 55 kilograms. And that would leave the third one to be 45 kilograms, assuming that, mass is conserved, which is something we can assume. They have velocities as well. Velocity of A was 90 meters per second, and that was to the west. Velocity of B was 55 meters per second at 30 degrees north of east. And velocity C, of course, is our unknown. All right, so we have a couple of new momentums, right? The momentum of object A would be a total of 9,000 kilogram meters per second west. B would be 3025. Got this written down here. Yeah, 3025 kilogram meters per second at that angle still. I'm not going to bother to write it down. And then C is still largely unknown. So, always helps to draw out a diagram. So we know when we're done, we have to have a total momentum of 2,000 to the west, right? Which would be to the left in this case. I know that after the explosion, I'm going to do this in a different color, we have object A, which would be 9,000, right, to the west. We have object B, which is going to be 30 degrees north of east, so it would be back this way. And that is 3,025. And we know we have object C, which would take us back to, that was terrible, let's try that again. Object C, which would take us back to a total of 2,000, right? Because afterwards, we have to end up at the same spot we were at the end, at the beginning, right? So this is momentum of object C. So we have a similar problem to what we had before. If you notice, we have a triangle here, but problem, we don't know what this angle is. We can't say it's 90 degrees, so we can't just make a right triangle out of the business and call it good. What we can do is make perpendicular and parallel components. So, all right, we know that momentum A plus momentum B plus momentum C has to equal 2,000 kilogram meters per second to the west. We know that because we're done. That's law of conservation of momentum. We know that A has a momentum all in the horizontal. So we know that one, right? So we have a horizontal component, a vertical component, so all these things, right? So A plus, well, let me start over. I'm not explaining this very well. We know that this has to be our total horizontal. Our total vertical moment then, right? So this is going to be all in the x direction. We know that the momentum of A in the vertical is 0, so we can ignore that. And we know that the momentum of B and the momentum of C in the vertical has to equal 0, right? Because they cancel out. Because B is going upward here and C is going downward. So that's easy enough. Now we just need to figure out some numbers to put in there. Well, we know that A is 9,000 west, and that's in the x direction. We know that the momentum of B in the x direction will be a component of the momentum, right? We have to get this side, P, B, X. So we're going to get this side up here. And that's easy enough. We know the angle, right? We know the hypotenuse. This is a right angle because these are perpendicular vectors. So it's just a matter of trig functions, right? So to get B, it would be sine of 30 times the hypotenuse, 30, 25. So I get B in the x direction to be, oh, I did that wrong. I got off a line. This should be cosine of 30 to get the x direction. So let's see here. That would be 2620. And C, of course, is unknown. But I know the total, A plus B plus C, has equaled 9,000. So 9,000 equals, excuse me, not 9,000, 2,000. 2,000 equals 9,000 minus 2620 minus the momentum of C in the x direction. So, math wizard work, the momentum of C in the x direction would equal 4,380 kilogram meters per second. Okay, so that's part of this. We have to do the same thing for the y, right? Remember the y, we have components of B and C both in the y directions. Again, similar process. We have the angle here. We need to get the side across from it. So to do y, of course, P A y is nothing. There is no y component. P B y would be sine of the angle. This is where I got a little ahead of myself before. Times the hypotenuse, 30, 25. And of course, PC and the y is unknown, but we know that has to total up to 0. So evaluating this, that's what, 1510. That would be, so PCY would be negative 1510 then, because BY plus CY is 0. So that makes sense. So now, if we go back, we have our x component of C and our y component of C. We can get the hypotenuse of C, which is our total momentum in the C direction. So, math wizard time, a squared plus b squared is c squared. We know that, let me get to a clean screen here. We know that the downward component is 1510. We know the horizontal component is 4380. So a squared plus b squared is c squared to give us the hypotenuse. I get 4,630 kilogram meters per second. And that is my momentum. Well, of course, we have to figure out the angle here. We'll get back to that in a second. So the momentum, 4,000 of C, part C, 4,630 kilogram meters per second. And then to get the angle, of course, tangent of the angle is 15. I am having difficulties writing. Writing on an iPad is an acquired skill that I haven't really acquired yet. We'll get there. So tangent would be opposite over hypotenuse, or opposite over adjacent. Yeah. 1510 over 4380. So theta will be 19 degrees, and that would be to the south of east. And that holds true regardless. Of course, we're looking for a velocity, so I need to take my momentum, divide by the mass. Let's divide it by 45 kilograms. 5 kilograms. So I get my velocity of C to be 103 meters per second at 19 degrees south of east. And boom, there is your answer. All right, well, I hope this helps you out. If you have any questions, of course, get a hold of me, and we'll get through this. Have a good day.